Okay. Hi everyone. My name is Nicole Lloyd-Ronning. I'm an astrophysicist at Los Alamos National Lab and at the University of New Mexico, Los Alamos. Today I would like to talk to you about multi-messenger astronomy and how we're at the beginning of a new way to look at our universe, or new ways to look at our universe. So I want to start with defining what I mean. What is multi-messenger astronomy? This shows up in the news all the time now. It's a hot new term. What does it actually mean? So let's spend a moment to think about the ways that we learn about our universe and how is it that we try to understand what's out there. The universe sends us, or space, when I say the universe, I just mean anything beyond our Earth, right? When we look up and point our telescopes into space, or look up with our eyes into space, the universe is sending us information. It's sending us messages. And so what I want to do is talk with you about what those messages are. And I think the one that we're really used to is what we see with our eyeballs. That is light, or another name for light is photons. What I'm showing you here is a picture of one object that's seen in with different types of telescopes that see different colors or different energies of light. This is how we're used to understanding our universe. When I talk about a telescope, we're usually talking about a thing that collects light, and then we look at that light and try to understand where did it come from, how is it made, how does it relate to the object that we're looking at. So that's the message that we're most used to, that has been used in astronomy since, the beginning of time. Since humans began, we used our eyes as light collectors to understand the universe. That was the message that we're most used to receiving. But the universe sends us other messages. And another message it sends is a particle called neutrinos. Neutrinos are really tiny, really fast, really light particles that are made in different types of objects in our universe, like in stars, or at the end of a star's life when it explodes, or in fast jets that outflow from black holes, and lots of other ways, including from our sun, which is a star. This is also making neutrinos. This message is really hard to receive. They're really hard to capture. We can't point a regular telescope at it. We have to build big vats of special kinds of water, or look in hundreds of kilometers of ice in the Antarctic to watch one of these neutrino particles interact with our detector. So this is another type of message that we get. Again, a neutrino, it's a light particle that is made in different objects in space. Another message that we get from our universe are particles called cosmic rays. Like neutrinos, they're fast particles, but unlike neutrinos, they're very heavy. They're and heavy in the sense compared to neutrinos. They're still teeny tiny atomic particles, but they're much more massive than neutrinos, and they're also made in very explosive, energetic events in our universe, like dying stars or black holes with material around them. Make these really energetic particles, and they fly toward the Earth from the farthest reaches of the universe, and they hit particles in our atmosphere, in Earth's atmosphere, and create the shower that you see here. So this shower of other particles that then we collect with special types of detectors. So this is another message that our universe sends us. And finally, the last one, which I'm going to spend a lot of time talking about today, is the message of gravitational waves. These are ripples in the fabric of space-time. This is a brand new way that we are looking at our universe. They've always been around, but we haven't been able to detect them until very recently. So I'm going to go into that a little bit later, but I want us to start with this picture that we see the universe in many different ways, not only with what we're used to through light, but also through these particles like neutrinos and cosmic rays, and these ripples in space-time called gravitational waves. And the last thing I want to mention about this multi-messenger, I want to show this picture a little more closely and emphasize again, this is one object that is seen in light of different energies. So for example, here we're looking at it in X-rays, and here we're looking at it in radio light, which is really low energy light. And again, back to the X-rays. And notice how differently it looks when we look at it with telescopes that see different types of light. Think about this as we talk about multi-messenger astronomy, that the universe looks different. We learn different things. We get different information and new important information when we look at it, through these different messengers, right? Through these different windows that we've opened up to try to understand our universe. Okay, so with that in mind, I'd like to move on to talking about a little bit more about what gravitational waves are. Let's spend some time talking about this message that the universe gives us, because it's a new one. It's phenomenal that we can actually detect these things, and there's lots of exciting stuff coming out in this field right now. So let me ask you to think about our universe as a kind of a flexible fabric. As like a sheet that you can stretch, like maybe you have a trampoline or something like that. Think about the universe as not just kind of empty space, but really this fabric. So things in our universe, and when I say things, I mean really anything like stars, planets, black holes, galaxies, which are collections of 100 billion stars, anything in our universe warps this fabric, which we call space-time, and it changes its shape. So here is a picture in 2 dimensions of heavier things warping the fabric more than lighter things. Okay, so what I'm about to say to you here is what's called general relativity. Maybe you've heard about this. Albert Einstein created this theory in the early 1900s, and it's got a fancy name, but this is all of general relativity summed up in one sentence. And that is, mass or energy tells that space-time fabric how to warp, and then the space-time fabric tells mass and energy how to move. So let me show a picture of that if those words don't speak to you. So again, in 2 dimensions, or you can imagine like a trampoline with a bowling ball on it, and then you roll a marble past it. And so the big bowling ball in the middle is warping the space-time fabric. And then anything that travels around that space has to follow the fabric. That is space, that we are moving, things move through space. So that blue ball is responding to the warping caused by the yellow ball. So the yellow ball is the first part of the sentence, mass and energy tells the space-time fabric how to warp. And then the blue ball is the second part of the sentence. The space-time fabric tells mass and energy how to move. And this is a 2-dimensional, a flat sheet visual of this, but up in the corner, you'll see we live in 3 dimensions, 3 spatial dimensions. And so that's kind of a visual in 3D. And I haven't said it yet, but if you think about it a little bit, the heavier the things are, the more warping you get. And if you think about what you might have learned or your experience with gravity, the heavier things are, the more gravitational pull they have. This way of talking about space-time and thinking about the warping of space-time is simply talking about gravity. This is how, when we talk about gravity, this is gravity, the warping of space-time. Okay, so certain types of motion through our fabric or in our fabric, space-time fabric, can cause ripples in this gravitational waves. Okay, so this is sort of a visual of how they look. They're a little different than a light wave. They're not, you know, an up and down in one direction. They're kind of a squeezing and squishing in two directions. This is, again, a gravitational wave, a ripple through that space-time fabric. So what's been really exciting in the last 5 years, and in fact, Nobel Prizes have been given for this work, is that we've seen these ripples in space-time. And so I want to tell you a little bit about how we detect the ripples before we go on to from what we've seen these ripples, okay? So this is something called the LIGO detector, and these long arms hold lasers that are a kilometer or even I think they're about a kilometer long, each of them. And they're 90 degrees from each other, and they're exactly the same length. And we have one in Washington State and one in Louisiana. And let's go to this visual here. So when we're looking for gravitational waves, let's look up in the upper left of this slide. When a gravitational wave goes by, it ripples space-time, and that means it squeezes it in one direction and stretches it in another. So the distance that these lasers are measuring will shorten along one direction and lengthen along another. And so what this gravitational wave detector does is exactly, very precisely measure the distance from this, what's called this beam splitter mirror, or this beam splitter to the mirror, and just constantly monitor that. And so let's see, when no wave is detected, the light waves from the lasers add up a certain way. And when a gravitational wave goes by and that distance is squeezed in one direction and lengthened in another, the light waves from the laser line up in a different way. So this is the essence of how we detect gravitational waves, how we detect a ripple going by. It's a really, really, really amazing engineering feat, because the precision with which they have to measure that distance over 1 kilometer is more precise than anything we've ever measured in any laboratories on Earth. It's like measuring the distance to our nearest star, which is Alpha Centauri, which is 4.5 light years away, millions and millions and millions of miles away, to within the precision of a human hair. So it requires extreme accuracy and precision, and it's really an amazing thing that this thing was built. And amazingly, we've been able to use this detector to see these ripples in space-time. So now I would like to talk about some objects that we detected through this messenger of gravitational waves. And what I want to do is show you a movie of two black holes colliding. This was in 2015, was the first time we saw these ripples in space-time in this LIGO detector. Two black holes were spiraling around each other, and they were losing energy as they caused the ripples in space-time and getting closer and closer together, until eventually they got so close they squished into a single black hole. And when that happened, you saw all the wiggles around that. When that happened, we saw in the detectors in Washington and in Louisiana, we saw this stretching and this expanding of space, this wave go by, this ripple go by, in exactly the way that was predicted by general relativity and Einstein's theory of general relativity. Even more exciting to me is that we've combined messages. We've really exploited the use of this multi-messenger concept of looking at the universe through different windows. So we've seen gravitational waves from two neutron stars smashing into each other. Now, a neutron star is what you get right before you get a black hole. It is a star that is more massive than our sun. It's about 1.5 times the mass of our sun, but it's squished down into a sphere that has a radius of only 10 kilometers, so of a small town, like the town that I live in. So it's this really, really, really massive thing in a really small space. But it hasn't quite yet gotten to that next level of being a black hole, where you kind of rip space, the space fabric. So it is kind of the last step before the black hole. And we watched these two neutron stars swirl around each other, ripple space, create these gravitational waves. But in addition, they also created a flash of light. That when they collided, they not only rippled space, but they gave off a whole bunch of photons. And this then allowed us two windows into this object, not just the light, not just the gravitational waves, but both. And combining this gave us lots of information about a lot of important things, which I'll talk about in a second. So the gravitational waves told us, what are these things colliding? They told us they are two of these very dense small stars smashing into each other. The light that we collected from this event then told us something about where we come from. So maybe in your classes you've seen this thing called the periodic table, which basically is a summary of all of the atoms that we know of in our universe. The atoms, the elements is another word for it. So we know where most of the low number elements come from, the ones at the beginning, 1 through 26. We know that those are made in stars. We have a good idea where most of the lower number elements come from. But these higher number elements, and when if you're not familiar with the symbolism of the periodic table, let's look at, for example, number 79, which is Au, that is gold, and 78, Pt, which is platinum. So these are elements that we mine here on Earth. We have these elements that exist in nature. We see them, they exist, but we don't know how they were made. This has been a long-standing problem in astronomy, is how are these heavy elements, which is another term for these elements that have high numbers on the periodic table, how are they made? That we can't figure out a way to make them in stars like the lower number elements. So how are they made? And in particular, I do want to focus on the gold and the platinum. Okay, and so I want to pause for a moment and remind you why we even care. Besides just wondering, I'm just curious, how did gold get here? Where did we get the platinum from? Where did it come from? Let's remember how we use these things in our daily lives. I'll put both of these up. So on the left, I have a picture of platinum. And besides in really nice jewelry, we use it in our cars, in catalytic converters, in fuel cells, in our computers, in hard drives. It's used in pacemakers and even in some cancer therapies. Gold, again, besides being used in jewelry, we use it in banking we use it in wires and circuits, in dentistry, in surgery. It's used often on satellite construction. So these are elements that, not only might you wonder where do they come from, but also we use them in our daily lives. And to me, that makes the question even more urgent to understand, how did they get here? Where were they made? And it turns out that we found out from the light in those neutron stars colliding that those elements were made in that event. So we collected the gravitational waves and the light from the neutron star collision, and the light had signatures of gold and platinum. So it gave off a type of light that gold would give off and that platinum gives off. And so from collecting that and then combining it with the gravitational wave information, we could say that the heavy elements on our periodic table were made in these neutron star collisions. And I'll remind you also that we are made up of some of these heavy elements, and life evolved because of the existence of some of these heavy elements. So we might be able to say that we're here because of these neutron stars merging. And we've learned this, we've gotten this clue into our own existence from this multi-messenger astronomy. from looking at different messages that space sends us. And with that, I'll just show you an image of a black hole, and I'll stop there. Thank you.